right, in Chapter 7, we're going to talk about the thermodynamic principles that govern chemistry, and we're going to relate it to a lot of the stoichiometry concepts that we talked about in Chapters 4 and 5, and also we're going to relate it to gases. So we need to understand first the idea of endothermic and exothermic reaction. So an endothermic reaction is a reaction type that is going to gain energy. So the reactants have a lower energy than the products. So the difference in energy will be positive, going from products minus reactants. Exothermic means heat is released by the reaction, meaning the change from final minus initial is going to be negative. So the energy of the reactants is higher than the energy of the products. So to understand energy as a whole, what is it? So energy is anything that has the capacity to do work. And what is work? Work, based on physics, is force times distance. So it's a force that acts over a distance. There are different types of energy. There's kinetic energy and potential energy. Those are the main types of energy. So kinetic energy is the energy of motion. Potential energy is the energy that is potential. So it is a potential to form kinetic energy. And examples of potential energy are chemical potential energy, which is stored in the bonds, ionic or covalent bonds. And also we have nuclear energy, which is stored in the nucleus. And a nuclear reaction releases that nuclear energy. For kinetic reactions, or for kinetic energy, we have thermal energy, which is the energy associated with a change in temperature. And like we talked about in Chapter 6, the kinetic energy, the average kinetic energy, is the temperature, right, is a representation of temperature. So that's what thermal energy relates to. It relates to the change in temperature and the motion associated from the change in temperature, the motion of the particles. So here's potential energy is the energy stored in an object or the energy associated with the composition or the position of the object. So in kinematics, we have potential energy as mgh. So here's different types of energies. We have kinetic and potential, and with kinetic, we have thermal, and also we have electrical energy. So here's another one we'll talk about. Electrical energy is associated with the flow of electrons, so that's in motion as well. And then we have, for potential energy, nuclear, which is potential energy stored in the nucleus of atoms, and chemical energy, which is stored in the bonds. We also have light energy, which is a form of kinetic energy, the movement of photons. We'll talk about that more in Chapter 8. Another thing to define are the system and the surroundings. So we're going to be talking about the energy or work done on a system. Now, a system is the body that is of the chemical reaction. For example, or any reaction. For example, if I push a chair, the chair is the system. I will do work on the system. And the surroundings will, I am the surroundings. The surroundings will do work on the system. We define the surroundings as everything else at which the system can exchange energy with. So really what's happening in the world is there's a constant energy change between an ever-defined, ever-changing definition of a system and a surrounding. So the surroundings could be the universe. The surroundings could be everything that's not a chair. You know, it could be, it all depends on what we define it as. So and that's what thermochemistry is, the study of exchange of energy between the system and the surroundings. And we define the system all the time, and that changes. Units of energy. We've seen the joule before, and a joule is 1 kilogram times meters squared per second squared, also 1/2 mv squared. But we also have another unit called calorie, and calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So it's a standardized unit, and a joule is the amount of energy needed to move 1 kilogram 1 meter. So 1 kilogram per meter squared per second squared. So we also have another unit of calories. So we're familiar with calories based on food. This calorie is actually different than the calorie needed to raise the temperature of 1 gram of water by 1 degree. The capital C calorie is otherwise known as a kilocalorie. This represents 1,000 of the little calories. So what we could say is that 1 kilocalorie, which is the calorie that you eat in your food, one of those is the amount of energy needed to raise 1 gram of water by 100 or by 1,000 degrees, or raise 1,000 grams of water by 1 degree. So here's what that equals. So 1 capital calorie or kilocalorie equals 1,000 little calories. We also have the kilowatt hour, which is for electricity, but we're not going to really talk about that one. So here's our kilocalorie. So in any nutrition facts, I guarantee you the calories will be capitalized, and this stands for kilocalorie. And the reason why we use that is because it's easier to say calorie than kilocalorie every time. So we mentioned we have this energy exchange between work and heat of the system and the surroundings. So we have a constant exchange of heat and work. So first we want to understand what a state function is. Now, a state function represents a change in state. That the change in state is the only thing that matters with a specific function we're talking about. For example, energy is a state function. So what we mean is that let's say we have two paths going up a hill. And one path is 12 miles, but it's less steep. One path is 5 miles, but it's more steep. The energy required to take either path is the same, because all we care about is the energy to get to the top. It's the same thing as running and walking. If you run 2 miles, you are going to use energy faster, which is going to heat up your body more. But if you walk those miles, you're going to use the same energy just over a longer period of time. So getting from state A to state B, or place A to place B, getting from point A to B is going to use the same amount of energy, but the time might differ. So it doesn't matter which path you took. It only matters where you end up. That's what the definition of a state function. So energy is a state function. So it's E final minus E initial. The only thing we care about is the final and the initial states. So we have this definition of internal energy is the summation of Q and W. Q is the amount of heat energy that is either gained or lost by the system, and W is the work gained or lost by the system. It's a function of force per unit distance. Now, if you walk versus run to a spot, the distance will be the same, but the force that you generate on the floor, let's say, the force on the surroundings is going to be more, meaning that W will be more negative. But the heat, since you are the system, you will gain more heat comparing that to walking. So you'll have a higher positive Q and a lower negative W. That's if you run. If you walk, your W will be a kind of a higher negative, and then your Q will be lower positive. So if you add those values together, your delta E would be the same if you walk or run. So you have two non-state functions which add together to make a state function. We also have the first law of thermodynamics, which is the law of conservation of energy. Similar to the law of conservation of mass, cannot be violated. And we can use this delta E equals Q plus W to calculate delta E for any given reaction. So we have heat and temperature. So heat is the exchange of thermal energy between the system and the surroundings. That is this Q value. Temperature is the measure of that thermal energy. And we can relate the two based on the heat capacity of an object. So depending on the type of object, the rate at which that object changes temperature with given energy differs. So for example, this is called heat capacity. So if you have water has a high heat capacity, meaning it will take a lot of energy to change the temperature of water. But that same amount of energy on a rock or on sand will change the sand by a larger degree of temperature because it has a lower heat capacity. And here's a great example. If you put 1,000 joules of heat energy onto 100 grams of sand, it will raise it 12 degrees, but it raises the temperature of water only by 2.4 degrees. And a great example of this is the beach. If you go to the beach in June, the water might still be pretty cold, but the sand is hot. And that's because sand does not take much energy to change temperature, and it has a lower heat capacity than water. And again, this specific heat capacity is different for every object. Usually metals have a low heat capacity. Some other materials have a higher heat capacity that have intermolecular bonds, and like water has strong hydrogen bonds, so that has a higher heat capacity. We also have the molar heat capacity, which can be factored in that could be factored in the molar mass. So we can take the molar heat capacity, which equals the specific heat capacity, times the molar mass. So we know that what is the amount of heat energy required to raise 1 mole of substance by 1 degree. And we can use this molar heat capacity, and we can use the heat capacity in general in this equation. So Q, which is the heat of the object, equals the mass of the object times the specific heat capacity constant, which will be given, times the change in temperature. So here's an example of that. We can find delta T, and for delta T in this case, since we have Celsius, we can just subtract the units, or we can convert both of those temperatures, -8 and 37, into Kelvin first, and then subtract them. Either way, it's the same because 1 unit Celsius equals 1 unit Kelvin. We then have 3.1, so we can plug that directly in, and we have our specific heat capacity that can be plugged in, and we get our joule number. So if you have a change in, if you are submerging an object, and this you might do in lab, or you might have questions on homework or the exam, if you are submerging a hot metal object into water, and you are trying to define the specific heat capacity of that object, and it's thus getting its definition, what metal it is, you can figure that out based on the mass of the metal, the specific heat capacity of the metal, which you will try to find, the change in temperature of the metal, the change in temperature of the water, the mass of the water, and the specific heat capacity of the water, making that equation, that Q equals mc delta T, otherwise known as Q equals MCAT equation, make 2 of them equal to each other, 1 for the water, 1 for the metal, and then you can solve for the unknown. And this can be given, there will be a lot of given information for you to do this. You could then relate pressure and work. So W, we know that delta E equals Q plus W, but also W equals negative P delta V. Where have you seen this before? PV, right? PV equals nRT. So we can say that P delta V equals negative nRT. So we can use this work to figure out our P delta V. We can then use enthalpy and heat. So enthalpy is the heat of a reaction. We can then use this heat of a reaction, otherwise known as delta H, in a stoichiometry way to figure out the change in heat for a certain reaction or certain moles of reaction. Now this delta H, it follows the same rules as if you are gaining or losing energy in a reaction. So if delta H is negative, it is an exothermic reaction. If delta H is positive, it is endothermic. So we know by this general reaction that if we have propane, which is C3H8, 1 mole of it will have a 1 mole of combustion of propane will have a delta H of negative 2044 kilojoules. So what if we have 50 grams of propane? That means we can take 50 grams, divide it by the molar mass of propane, we get the moles. We know that 1 mole is delta H equals negative 2044. So what is the delta H for 50 grams? We can figure out the moles and do that stoichiometry. So it's just a conversion factor. 1 mole is the delta H. Here's another example where of this reaction, 1 mole, delta H is negative 124. What is the value of delta H per mole of the reaction given if we know that 10 grams is negative 124? That's what it's asking. So we could then do the opposite, where we would find how many moles of the N2O4 would be responsible for creating delta H equals negative 124, and then we can correct that for a mole. So this enthalpy is the heat of a system, and it's the internal energy plus the PV. This is another definition that may not be given to you on an exam. So this is the enthalpy. And then we have the enthalpy change, which if we have a constant pressure, delta H equals the Q, meaning the heat of the reaction at a constant pressure. We know about endo and exothermic. So we have a combustion reaction, we have a delta H per mole of what is being combusted, and then we can correct that for any stoichiometry or any amount of grams, in this case kilograms, 13.2 kilograms, we can find the moles, then we can multiply that by our grams per mole of our enthalpy, our heat per mole of enthalpy to figure out our heat delta H of the sample. So Hess's law, another important concept. So what we can do is when we change these reactions, normally we are given them in a standard form. If we multiply a reaction by 2, we change the delta H by multiplying it by 2. If we flip a reaction, we make the delta H the opposite sign, because if a reaction is endothermic in one direction, the opposite direction is going to be exothermic. So that change and that sign of delta H will flip. And why is this important? Because we are going to be given questions where we can find the delta H of an overall reaction from the reaction mechanism. Now, we weren't really introduced to reaction mechanisms, but basically reactions don't happen, or some reactions do not occur of just the reactants adding together. They make one change and they become the products. Usually there's multiple steps of intermediates that are formed before the final reaction is finished. So what we can say is that the delta H of all of these added intermediate reactions equals the delta H of the total reaction. This means that delta H is a state function, meaning it doesn't matter how many intermediates we have, the delta H for the entire thing, the change in heat from the beginning to the end, no matter what happens in the middle, is going to be the same. So we have the standard enthalpy change, which is the reactants in their standard states. So this means that pure gases are exactly 1 atm, pure solids or liquids are 1 atm, and we have a 25 degrees temperature, so that's 298. Substances in a solution have a concentration of 1 molar. And we have these standard delta H's of formation and of any given compound that'll be given to us. So what we can figure out and how we can calculate a delta H of a reaction from looking at one specific reaction is we can take the sum of the delta H of formation of the products minus the sum of the delta H of the reactants. So for example, if we were to figure out the delta H of the reaction of this reaction in blue, what we would do, and this is not on the slide, what we can do is we would say 2 times the enthalpy of formation of H2O plus the enthalpy of formation of CO2, take that number, minus the reactants, which would be the delta H of the formation of CH4 plus 2 times the delta H of O2. So we take those numbers and we do the products minus the reactants. So for Hess's law, what we try to do is we are trying to find the enthalpy of formation of this reaction. Another way to do it, if you don't have the enthalpy of formation of each one of the products and reactants separately, like to do what I just did, products minus reactants, but we had the reaction mechanism, what we can do, and this is the reaction mechanism that will be given, we can say, all right, how do I make these 3 steps look like the top? So first we need to find our reactants and our products and try to make them in the correct positions. And this is kind of fun. So CH4 is in the first reaction on the right side. We need it to be on the left side. So this reaction will be flipped. If we flip this reaction, the delta H will be multiplied by 1. So -1 times. Now we need 2 O2. Now the O2s, there's one on the left here and one on the left here. That's good. CO2. We would, if we keep the second reaction where it is, we have 1 CO2 on the right. That's also good. And then the 2 H2O, we're good there as well. So we only need to make a change to the first reaction. This is very easy. But in other examples, we're going to have to make changes to multiple reactions. So if we do that, we take the negative sign of that, and then we simply add everything together. So here's a more complex Hess's law problem, and you'll have a lot of practice on this, where you are trying to determine or calculate the delta H for the reaction below when you're given this reaction mechanism. So what you can do is, very simply, you can look at where everything is supposed to be. We need 3 NO2 on the left. If we look at this mechanism, let's try to find NO2. We have 2 NO2 on the right. So this reaction needs to be flipped, and it needs to be multiplied by 3 over 2, meaning we multiply the delta H by -3 over 2. Then for H2O, we have 1 H2O on the left. Where's H2O? It's in reaction 2, and there's only 2 of them, or there are 2 of them on the left. This means the reaction needs to be divided by 2, which means we multiply the delta H by 1/2. And then we have, in the product side, we have 2HNO3. That would be taken care of by doing that second step. So the second reaction, we would be dividing it by 2. So that would become 2HNO3. So that's taken care of. Now the final product, which is NO, if you look at the third reaction, there is 2 NO on the product side. So this reaction, but wait, if we flip this reaction, the top reaction, like we were going to do, and divide it by, or multiply it by 3/2, you would create 3 NO on the right side. If you have 3 NO on the right side, and if we flip the third reaction, we will have 1 NO on the right side. That means, again, this NO2, since we are flipping the reaction, it will be now on the right side. And we are multiplying it by 3/2. So 3/2 times 2 is 6/2, otherwise 3. So we're going to have 3 NOs on the right. And just like algebra, to have 3 NOs on the right, and then if we flip the bottom reaction, this third one, we will have 2 NOs on the left. So 2 NOs on the left, 3 NOs on the right. That cancels out, so no NOs on the left and 1 NO on the right. This is why we have our 1 NO. Then, after we make those modifications to our delta H's, we simply add them up, and we come up with our total delta H. So that's how you do Hess's law. We're going to do a lot of examples with that in class. And last but not least, we have calorimetry. So we have different ways of determining the energy of any substance by burning it. So we have a bomb calorimeter, which has a constant pressure, and we can determine the change in internal energy from burning a sample. So this is how you calorimeter. You determine the amount of calories something has by burning it. And we can use our QC delta T reaction equation. And since we will not have mass into this, we got another way of writing it is Q equals C delta T without the M. So we have our Q equals MC delta T, and also we have Q equals C delta T. That can also be used. All right, that is it for Chapter 7. If you have any questions, please comment below, and don't forget to like the video and subscribe for more.